Hello everyone, welcome back. This is the second part of our discussion of acids and bases. This is Dr. Rhonda Kofelt. In this part we're going to look at several things, aspects of acids and bases, but we're specifically calculating some OH and H3O plus concentrations as they are related to each other and as they are related to the ion product for water, Kw. So oxyacids are acidic hydrogen atoms that are attached to an oxygen. Okay, so for example, you've got sulfuric acid, which has your acidic H's, and then it's attached to these oxygens. Nitric acid's the same way. It is attached to an oxygen in its formula as well. The more electronegative the Y part, okay, that's actually attached to the other side of that oxygen is, the stronger the oxyacid is. And so as you go down a group or a column, the acidity of these oxyacids is going to decrease. So it's the same trend that we saw in the binary acids. Also, the larger the oxidation number of the central atom, the stronger the oxyacid. So H2CO3 would be a stronger acid than H3BO3. So the acidity of these increase as you go left to right. So it's which is the opposite trend of the binary acids. So the more oxygens, and this is the one that's really going to be helpful to you, I think, the more oxygen atoms that you have attached to your nonmetal, the stronger it is. Okay, so if you've got an O3, that's going to be stronger than an O2, which will be stronger than something with just one oxygen if it had it. Or if you have 4 oxygens, that's going to be stronger. Okay, and so it's just showing you've got, we're using the chlorine, so we've got perchloric acid, and we've got chloric acid, and then we've got hypochloric acid, and so this is strong, weak, and then very, very weak. And so we have electronegativity values that are associated with the Y. So for example, chlorine is a 3, bromine is a 2.8, and I is a 2.5. And so you're going to, even though all of these are technically weak acids, as you go down in that column series, your electronegativity goes down. Therefore, your Ka, okay, your equilibrium, if you want to think about it that way, equilibrium constant for your acid is also weaker or lower. So when we put these things in water, they're going to ionize. It's called hydrolysis, right? And so if you have a strong acid, the strong acid is going to produce a strong electrolyte because it's going to completely ionize. So a strong acid will completely ionize into H plus and then plus whatever its anion is. A weak acid is a weak electrolyte because only a very small percentage will hydrolyze. So when you get done, you will still have the molecular form of whatever that was. Okay, so at equilibrium, your H plus is not, you're not going to have 100% H plus of what you started with in the weak acid. In a strong acid you would. And the electrolyte means that the electrolyte is going to be stronger the more ions you have in solution. And so if you've got lots and lots of ions, in the case of a strong acid, you're going to have a strong electrolyte. If you have very few of these and mostly this left, this molecular form won't carry electricity. So your electrolyte is going to be very weak. Strong base, same way. Strong base is going to be a strong electrolyte because it's going to produce a lot of those, almost 100%. And then a weak, for the same reasons, very few of these OHs, and then whatever the other component was, the cation was. So if you have a strong acid, it's going to make a strong electrolyte. If you have a weak acid, weak electrolyte. Strong base, strong electrolyte. Weak base, weak electrolyte. So a strong acid is going to have a Ka, okay, an equilibrium constant basically, greater than 1. So since strong acids donate almost all of their hydrogen atoms and have 100% ionization, then they are going to be a strong electrolyte. So you're going to have a high concentration of your H3O plus. And so when you're figuring out how much H plus you produce, when you put it in water, it's going to be the same as what you started with. So whatever the molarity of your acid is, when you put it in water, you're going to have that molarity of your H plus. There are 6 strong acids that we're concerned with, okay? And with these 6 strong acids are hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. Okay, and so those are the 6 that you need to know, because if you know the 6 strong acids, then anything else you see is going to be a weak acid. So you don't have to memorize the thousands of others. Weak acids are going to have a Ka that's less than 1. Okay, so times 10 to the minus something. They only donate a fraction, so they're partially ionized, and so they still have some of their HF left, even though they ionize a little bit into H3O plus and F minus, they're still going to have quite a bit of HF left in there. That's one of our weak acids. Notice that's the only halogen that is not a strong acid. So examples of common weak acids are vinegar, acetic acid, carbonic acid, formic acid. Remember me telling you about this carboxyl group, COOH, okay, that is what you look for. You can easily identify those, or any other organic acid that you see. But remember, if you know the 6 strong, then you don't have to know the others, because all the rest of them are weak. So the acid ionization constant, K sub A, you can think of it as an equilibrium constant, okay? The farther the equilibrium lies toward the products, the stronger the acid or base is going to be, because you are producing more of these hydronium ions. And what makes something acidic is the presence of these hydronium ions. So the more you have, or the higher concentration, then the more acidic the pH is going to be. The equilibrium constant for the reaction is called the acid ionization constant, K sub A, because it's an acid, so it's got an A. Remember, we've seen KCs and KEQs, and they're really all interchangeable, except you just use these to make sure you're identifying that it's for the acid. And the larger the value, the stronger the acid, because that means you're going to have a higher concentration of products than you do reactants. So the top number is going to be higher, which makes the overall number bigger. Okay, so the Ka's for these are we're going to only look at aqueous and gases, right? Liquids are left out of the Ka expression. They do have, as we saw in the other chapter, an effect on equilibrium sometimes, but they do not change, so they're not in the Ka expression, just like they weren't in the Kc expression. And so you just take the products over the acid, and that's going to give you the Ka. And here's just a chart of the different ones that we talked about. Notice that your Kas, you can get really small, and these aren't even as small as some of the smaller, 10 to the minus 19 and things like that. But notice that I kind of got them in order going down, and chlorous acid, 1.1 times 10 to the minus 2. It's a weak acid because it's less than 1. if that Ka is a whole number, okay, if it's a number above 1, then that means it's a strong acid, and we know there's only a few of those. So usually you're only going to get a Ka for the weak acids. Notice that the pKa is the negative log of Ka. That's how you get that pKa. So water is a really cool thing. It's what we call amphoteric. And amphoteric molecules can act as either an acid or a base. Therefore, there must be a few ions present in order for this to occur. So about 2 out of every 1 billion molecules form ions. Yeah, I know, it's not much. And that is called the auto or self ionization of water. So the auto-ionization of water is where you have a water molecule that basically ionizes into H plus and OH minus. And remember me telling you that H plus is used interchangeably with H3O plus. Where H3O plus comes from is if you've got 2 water molecules that are adding together, you're going to produce H3O plus and the OH minus. So either way you want to do it is fine. I normally do H pluses just because it's easier to balance. You're not worrying about, those extra atoms. All solutions contain both H3O plus and OH minus if they are in water, if they're aqueous, okay? They all have both. If it's pure water, then the concentration of the H3O plus and the OH minus are equal. So the concentration in molarity is equal in H3O plus and OH minus. And they are both 1 times 10 to the minus 7. And that's, of course, at room temperature. Everything, depends on the temperature. The product, okay, which means you multiply them, the product of the H3O plus and the OH minus concentrations is always 1 times 10 to the minus 14. That number is what we call the ion product of water, W for water. At least it makes sense, right? W for water. All right, and again, that's at 25 degrees C. Temperature does change pH. So that's why we always try to take pHs at the same temperature and immediately, like after you take a sample or whatever. If you measure one of those, okay, so if you know the H3O plus, for example, you can easily calculate the other one because you multiply them together to get the 1 times 10 to the minus 14. And so this ion product of water, also called the dissociation constant of water, which because of the auto-ionization, right? It gives us a way to compare these two numbers. As the H3O plus increases, the OH minus must decrease so that they're always equal to the 1 times 10 to the minus 14. So this one times this one is always equal to that. So if I only know one of them, like if I know this one, then if I want to know what the other one is, then I just divide 1 times 10 to the minus 14 by whichever one I know, and that'll give me the other one. Because they always have to change to maintain that Kw, that constant ion product. So neutral solutions, that is pure water, have equal H3O plus and OH minus. Okay, so each one of those is 1 times 10 to the minus 7. If they are acidic, then your H3O plus is going to be higher than the OH minus. And in basic solutions, the OH minus will be higher than the acid. And that makes sense because if it's a basic solution, that means it has more OH minuses. If it's an acidic solution, it's going to have more hydronium ions, because that's by definition what causes them to be acidic or basic. Okay, so let's look at some of these problems. I'll give you this example first. And so this is calculating the concentrations by using this relationship of the Kw. So we know that H3O plus times OH minus is going to be 1 times 10 to the minus 14. All right, so in A, our hydronium ion is 7.5 times 10 to the minus 5 molar. And we know that that times hydroxide is going to give us 1 times 10 to the minus 14. So if I'm solving for that, I'm going to divide 1 times 10 to the minus 14 by 7.5 times 10 to the minus 5. Those are both molarity, right? And that is going to give me 1.3 times 10 to the minus 10 molar. And I'm doing the hydroxide concentration, right? Now, the hydroxide concentration, if it's higher than 10 to the minus 7, right? And remember that 10 to the minus 1 is 0.1, and 10 to the minus 2 is 0.01, and 10 to the minus 3 is 0.001. So as those numbers get higher, that your concentration is as your exponent, gets higher, that means your number is actually smaller. So this is a small, because it's lower than 10 to the minus 7. So this one would be acidic, because I'm looking at the hydroxide, and the hydroxide concentration is less than 1 times 10 to the minus 7, so it's acidic. In the second example, we're doing all these, we're doing the hydroxides. I'm going to go ahead and because now we know how we've rearranged it, the hydroxide is going to be 1 times 10 to the minus 14 divided by the hydronium ion concentration, which is 1.5, times 10 to the minus 9. You turn the page. And that gives us 6.7 times 10 to the minus 6. And to decide at this point if it's acidic or basic, all you have to do is look at this, okay? It doesn't matter what that number is. So it's to the minus 6. So 10 to the minus 6 is a bigger number than 10 to the minus 7, okay? Therefore, you got more hydroxide than you do hydronium, so this would be basic. All right, and then C, you have this time to get the hydroxide is going to be 1 times 10 to the minus 14 molar divided by 1 times 10 to the minus 7 molar. I don't even have to do that in my calculator. That's 1 times 10 to the minus 7 molar. And so is that acidic or basic? Neither. It's neutral. Because if that is equal to 1 times 10 to the minus 7, so is the hydronium, right? So they're both 1 times 10 to the minus 7. They're equal, okay, in this case. And that means it's neutral pH, okay? It's neutral, it's not acidic, it's not basic. And then your practice is to just go the other way, okay? You're calculating the hydronium ion concentration by doing it the same way by using the Kw. And so hydronium times hydroxide equals your Kw, and so you do it exactly the same way. You're just dividing by your hydroxide instead of your hydronium ion. So those are your practices, and those work exactly the same as that previous problem. So that's the end of this part, and that shows you how to do your calculations using Kw.